Hello. In this module, we will see competing risk modeling using R. In survival analysis, at the end of the study, patient status defined as alive or dead. Now, death, when is our main event of interest? In that scenario, it is very important to consider the reason of death. Since death is a permanent event, so reason of death is very important to be considered. For example, patient treated with cancer therapeutic regimen and patient died due to some other reason, due to like myocardial infections or pneumonia aspiration. Those reason of death should not be considered as event of interest, that is death due to the cancer therapeutic effect. In that scenario, it is becoming very important to consider reason of death from the study initiation to study data analysis. When we are going for planning the study, it is very important to consider the fact that reason for death should be considered and give emphasis separately. When you are going for analysis, it is also important to take matter how death happened. As I have seen in earlier modules that status of the patients at the end of the study coded as 1 if they are alive and 2 if they are not alive. Now these two can again be defined into two values like 2 and 3. If they really died because of therapeutic effect, then that can be defined or decoded as 2. Other reason for death, like we are saying that death due to pneumonia aspiration or death due to myocardial infection, like that, in that sense death should be decoded as 3. Now in that scenario, how to analyze the data, we will see in this module. Now here we will see how to do clinical trial data analysis using R. In clinical trial, more than one treatment given to the patients into two arms, and after giving the treatment effect compared in terms of parameters observed. This is the example data, and the analysis here we will perform on the library called multcom for multiple comparison. When we are having two treatment groups, then it is easy to compare, but in addition to two treatment groups, here we have taken 4 therapy, that is denoted as T1, T2, T3 and T4, and these are basically the therapy or treatment or arm provided to the patients to reduce their blood pressure. And as a blood pressure observation, diastolic blood pressure measurement taken for each patient after giving their therapy. So first variable here is defined as tree, where T1, T2, T3 and T4 assigned to each patient. Either they got T1 or T2 or T3 or T4, any of choice. Since this is a string variable, so inverted comma is used here to assign any variable here, and thereafter DBP assigned as a diastolic blood pressure, and after giving the therapy, the diastolic measurement of each patient has been taken as 110, 112, 113, that. So these two variables, that is treat and DBP, was assigned through a function called data.frame to a database MyData. So now here the database MyData is having two variables, one is treat, another one is P. Now after that we will call this database and compare the treatments, and what is the treatment wise difference on diastolic blood pressure. We will here in typically clinical trial we do consider two therapy, and based on these two therapy we do compare how parameters like diastolic blood pressure, systolic blood pressures having better. So the comparison generally be compared through the mean parameters, and here we will also compare the mean parameters, mean values between these therapy, and see how one treatment is better than other. Now my data, once I call my data, after that another function I used as a AOV, and within parenthesis dbp follows to treat is used, and again we call the data equals to my data. So in the my data, dbp and treatments are given here. dbp is considered as response variable and treatment is considered as the covariates. So since we are having 4 types in treat, so between these 4 types, what is the treatment wise difference, group wise difference that can be compared by the ANOVA, and for applying ANOVA we use the function AOV. So here AOV will compare the treatment group wise what is the dbp values difference. If this difference is existing, is it really significant or not, that can be observed through p-value. Now we are not going into results. Before that we are doing some others code, showing other code also. See, now into the library called multcomp we are assigning glht functions, and glht function will consider that results observed for applying these ANOVA on the my data as assigned in earlier slide as a my data.aov, and in my data AOV we will go for done it test here. See here linear FCT with the MCP of treatment equals to done it is being considered as an alternative, it is considered as less than. So what is the reason when we are having multiple groups? So it is when ANOVA perform, ANOVA in null hypothesis it assumes that treatment wise there is not any difference, but it is very difficult to find out in which treatment having more variation in others. Otherwise, not only that, if it is assumed that T1 mean equals to T2 means equals to T3 means equals to T4 means, when null hypothesis rejected, it is very difficult to state by applying only ANOVA that was the variation only or difference was basically based on any T1 T2 or T2 T3 T3 T4 or T4 T1, or the variation was only for between all the treatment therapy. So that is the limitation of ANOVA. So group wise difference presence or not, that can't be obtained through ANOVA. So to overcome that limitations, post hoc test can be used. Here in the library called multcomp we are using the done it test. Here the beauty of done it test, it's consider one group as a control group and other arm as cases ground, and with that others arm it compare the treatments and find out the difference is presence or not. Now once we consider the my data.mc, and after that we are calling the summary of my data.mc, we will see the results. In next slides we will show the results are coming, and once I had done, we will another function we will use, that is summary of my data.mc, and now this treatment test done considered as done, it will be replaced as test as Bonferroni. Will come how to what is the reason to consider the Bonferroni test, and thereafter we will take the my data.ci and we will see this confidence intervals for 95% confidence interval results of the point estimates variation will be observed, and thereafter we will go for plotting and these results, and a graphical expression we will see how these differences are observed, and later on we will go for a summary of my data.mc by applying this adjusted free test. Now the results obtained by applying the my data.aov, and AOV within parentheses the BP, that is diastolic blood pressure and treatments consider, and once we put the summary of my data.aov, it shows that treatment wise there is a significant difference present, as the p-value is coming 0.00105. So it shows that this treatment was having diastolic blood pressure difference on so therapeutic effect difference was there, but here it is very difficult to find out that which treatment was having different in comparison to others, or all the treatment were different from each other. So that can be difficult to state from this result. And for that we have to go for multiple comparison test, and that is one of the utility of considering the multiple comparison test in clinical trial data analysis. Now when we are having more than one follow-up observations and more than minimum two treatment arms, then it is also very difficult to compare the treatment effect through ANOVA. So in that sense we have to take other tools to analyze the data, but here we are going for simple procedure when we are having only one time observations, that is diastolic blood pressures taken in after follow-up study, single time observations, and we are having more than treatment one, and to comparison that. So now we will go for next slide, where we are going to see that results observed for applying the library called MALTCOM, and as a GLHT functions we are using these choice as a donest, that is inverted comma written as donate, and as an alternative we are putting as the less. So we are using that the alternative hypothesis that one treatment is having better mean value of diastolic blood pressure than others or not. So as a one-sided tail test we are, or one-sided or one-tail test we are using here. So definitely here our result will be obtained from one-sided, not for both-sided, and we will see that result that in the down of these slides is coming that T2 minus T1 greater than equals to 0 is considered. So if we can consider as not less than, as if you consider two dot sided, then comparison should be T2 minus T1 not equals to 0. So here that is the choice we have considered for illustration purpose. So you may try also for two dot sided. Now we are going for these results. So as a result part shows that simultaneous test for general linear hypothesis. So multiple comparison of mean has been done by Dunnett contrast, and we had done with treat with AOV, that is DBP with treatment, and estimates of regression coefficient is obtained that for between treatment 2 and treatment 1 estimates is coming as minus 1.933 with standard error 4.36 and t value minus 0.443 with p value 0.747. When we are comparing T3 from T1, so comparison between third treatment and first treatment, the difference is quite high. Is coming from to 5.73 in comparison to earlier one, and that was minus 1.93 with standard error almost same, that is 4.36, and p value near to 1, that is coming 0.99. Now coming the treatment wise difference between T4 to T1, again it is coming 9.18 with standard error 2.45 and t value 3.74 and p value with 1, so almost same. And now the beauty of applying Dunnett test is that Dunnett test consider one arm as a control arm, and with respect to that arm other arms difference has been compared. Here the arm T1 is considered as a control arm, and in comparison to that control arm other arm T4, T3 and T2s were compared and simultaneously given the result. So that is the utility of the Dunnett test. So when we are having more than two arms and we want to compare individually arm to arm, then Dunnett test can be considered here. Now since in earlier we had given the summary of my data.nc as the results, now the same data set we are considering here, my data.nc with test equals to adjusted and type as a Bonferroni, and as a result it's showing that the difference between T2 and T1 is coming minus 1.933 with standard error 4.36 like earlier, but t value reduced to minus 0.443 with probability of, that is p value, is 1. So the utility of Born-Ferrari is that Born-Ferrari reduce the whole p value into 4 equal segment here, and based on that equal segment we will see the p value comparison here. Now it's when we are having more than 2 arms, like 3 to 4 arms here, also in a clinical trial data analysis, where and we want to make this arms are differing or not, and these it is very difficult to consider one p value over there. In that scenario, p value will be separated, divided into equal number of groups. In case here we are having 4 groups, so p value observed will be divided by 4, and that uniform p value will be considered for each treatment difference here, and based on that the result will come. So this is the another result obtained by applying the Born-Ferrari test. Now we are going to get this confidence interval of our estimates. Again we will see that my data dot ci and function conf int that will use to get the confidence interval of these regression estimates, and within parenthesis we are going to for my data dot mc with level 95% confidence interval, and calling my data dot ci, and this my data dot ci giving us this treatment wise comparisons confidence interval. So as I estimate, I have seen that T2 and T1 was coming minus 1.933, and this confidence interval is here is coming from minus infinity to 8.1477. And since we are doing for one arm, one sided test, so upper arm here is coming 8.1477 with confidence interval for, and that is confidence interval is 95% for T2 to T1 comparison. Again the comparison for T3 and T1 is coming minus infinity to 15.8143. Comparison for T4 to T1 is coming minus infinity to 14.85, and T4 to T1 is coming minus infinity to 39.0844, where the point estimates are, you can see the point estimates are between these corresponding confidence interval. So minus 1.933, 5.733, 9.1857 and 22.400. So these point estimates are coming their corresponding confidence interval, and next slide we will see how to plot this confidence interval graphically, and graphically we can find out this treatment wise comparison. So we are taking the plot of my data dot ci, and mains equals to inverted comma. So inverted comma, within inverted comma we may put any comments what we want to see in the graphs, that can be written as treatment wise comparison between DBP or something else as you like. So it's your choice. Main equals to inverted comma, and y limit is considered here as 0.5 to 3.5, and x slab is considered as is DBP. So as a result you can see the treatment wise T3 and T1 difference with its point estimates, T4 with T1 with its point estimates that given as dotted, and this range of confidence interval shows with corresponding arrow, and the third lines this entire difference between T4 to T1 is given, and the entire difference between T4 to T1 is with point estimates coming around 22. So that we are observed from this earlier slide. We will go to earlier slides again, and here also these confidence intervals coming around 39 for the interdifference between T4 to T1. Let's see what is the exact results that is plotted here. So here in this last 3 row, if you look, that is T3 to T1 difference was 5.73, and with upper intervals 15.81, whereas T4 and T1 was 9.18 with upper intervals 14.85, and interdifference between T4 to T1 was 22.40 with upper interval 39.08. So that is shows in this graph only. So graphically we may also show this result and also interpret from these results. Now I will go to next slide. For to get these results with as a type with free. So earlier we have seen with bond Fermi. Now we are using the type equals to within inverted comma free, and that within these results will give us exactly with the Dunnett test, and that we have also seen earlier. There is utility of Dunnett test, and again this Dunnett test, that is compared between T2 and T1, T3 and T1, T4 and T1, and interdifference with T4 to T1's results. So here as a result, Dunnett test is considered T1 again as a control group, and with this T1 control group all these results are obtained. So but here it should be check this the p-value between T1 with T2 is coming with 0.747. when we are comparing T1 with T3, it's coming around 1, that is 0.997, and almost same. There was not any difference between T1 from T4. There was 1 coming with p-value. So that is the results, that is the separated results from T1. So in this example we have seen that how to compare more than 2 treatments and make the results. So this can also be utilized in other area where we are having a problem to make drug treatment wise comparison, and we are having multiple treatment arms. So separately it's need to consider treatment 1 with treatment 2, treatment 2 with treatment 3, and like that. I think it will help you for others work also. In this module we have illustrated the how to handle multiple observations or repeated observations of each patients observed during the follow-up study, and as an software we have used R here. We have used library called Multicop to analyze the data. This library can be used to find out the treatment effect comparison where data considered repeatedly over time. I hope you enjoyed this session, and this module will help you for other analysis where similar kind of problem is there, where we are having repeated measurement and multiple drug to finalize the which treatment is doing better in comparison to other treatment groups.